Hmm. Okay. Mhm. No, surprisingly. Good afternoon. Okay, so good afternoon, everyone. Today we're going to talk about Lab 11, about a convolutional neural network. And then also still you can download this notebook from the OLE, okay? Here, this one, Lab 11. And also this morning I've talked about some demo of your project. So you can, no matter if you already done or you haven't started your project, I suggest you to watch the recordings of the lecture this morning and have a look at the demo. Actually, I almost provide you everything there. You just need to adjust some hyperparameters, and if you want to get higher mark, then you need to change the structure of the neural network. Okay, then let's start the content of today, Lab 11. So actually, this code, I have already talked about it in the previous week during the CNN lecture. Okay, but that was during the lecture. We haven't do any practice on it. So today we are going to have some practice for convolutional neural network. Okay. Okay. And okay, then let's go through the code one by one. Okay, so at the beginning, we need to download the data, the libraries. Okay, and yeah, let's just connect it first. So if you haven't set your notebook type, okay, you can choose the notebook settings here, and then change to T4 GPU. Okay, it's also free. And I think you can, okay, well, let's connect it first. Mhm. Okay. Why it takes so long time? Okay, we've connected. So it will show you the time that you can use. Okay, and then every time you used up this time. Yeah. Oh, I have 73 hours. Oh, doesn't matter. Okay. So every time you used up this time, your session will be terminated. Okay, and then you need to reconnect it. You need to wait for a while, maybe several hours, and then you can use it again. Okay. So let's first load the libraries. Okay, and almost the same with the previous time. The only difference that we import a data sets here. Okay, I will talk about it later. And then we need to we are going to use this CIFER10 dataset. Okay, this dataset we've talked about in the lecture in the previous week. So we directly use datasets. So these datasets is a library. Okay, so the function, the method dataset is a library that we import here, datasets, right? And in these datasets, we have a dataset called CIFER10. Yeah, and this is a built-in dataset. Okay, that's why you can directly use it. It has some built-in function that you can just load it. But like for our project, you need to load your data by yourself. Okay, that's why I provide you a demo about how to use a data loader. Okay, you can refer to the recording of the lecture on 3rd of April. That means this morning. Okay, so we just use the load data function in this library to load the data set. Okay, and then we also do some normalization, as always. So this I've talked in the previous, the lecture in the previous week. Usually, we need to normalize it by 255. Because we are using the RGB color. It's a colorful image, okay? We're using the RGB color. And when you set the color of the image, it's usually the red, blue, or green value are usually between 0 to 255. Okay, that's why we normalize it by the value, the maximum value of 255. Okay, then we just download the data. In total, I think we have how many datasets? We have 60,000 images, okay? And then this test and train image and test images is already splitted by default. We have I think 50,000 train image and then 10,000 testing image. Yeah. So if you just put your mouse on the variable, you can directly see the dimension of the array. Okay. Okay, then we just plot it. I think this is the whole code. I don't need to make any change here. Yeah. So what we are doing here is that we'll give some class name, but this class name is just for plotting here, okay? This class name is not used for training. This is just for demonstration on the figure. So it's like we create 25 subplots, okay? 5 by 5. You can say 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 by 5 subplot. And then we plot 25 figures, okay, 1 by 1. And then we use their class name as the label. The class name is the one we define here. And then train, how we get the class name? We use the train labels, right? The train labels we get from the dataset already. And then the train labels of the I sample. So this is for we have 25 samples. For example, we have 25 samples from 1 to 25. And then we get the labels here, or labels here. But you might notice here that there's an extra space of index of 0. This is because that they define this label as a matrix. We can do like the dot shape, okay? So we can check the shape of the train label. You can say it is a matrix. So usually if it is only 50,000 labels, we define it as a vector. So if we define as a vector, then it will be like something like this. The shape will be like this. So we don't have 1 here. Then it is a vector. Okay. So because it defines a 2-dimensional array, that's why we need to put an extra 0 here. So it means the first element in this array, in each vector. Okay. So we have 50. Each label is saved as a vector inside this matrix. And then we have 50,000 vectors. And then actually, there's only 1 element in each vector. That's why we just take the first one, the 0 one. Okay. Okay, then this label is corresponding to the names here. So we just print out the labels as the X label. Okay, so because this is the X-axis, this is the Y-axis. And then we just replace the X label with the string label. Like this is a frog, this is a truck, the deer, something like this. Okay, so this is just to check what we have inside the data set. Okay, then we can start to configure our neural network. So as usual, as before, we need to use the sequential method, models.sequential. Yeah, sequential method. And then we need to add some layers, right? And the first layer is a convolutional layer. So it is used for feature extraction from the original figure. Okay, so we use add layers. This I think you already know. So we've learned before. Conv. We use 2D conv. Okay. Because figures we have length and width, right? So we need to use 2D convolutional layer. Okay. And also I've mentioned in the previous lecture that if it is just like a time series, okay? So sometimes you have a time series of 1 channel, and then you can just use a 1D convolutional layer. Okay, but for figure, for image, we have width and height. So we need to use 2D convolutional layer. Okay, then let's see. This is a hyperparameter, 32. Doesn't matter. You can use any value you like. Okay. So here we use 32. And this is the size. 3 by 3 is the size of the kernel. Okay. 卷积核. Okay. This is important. Usually the kernel size is 3 by 3 or 2 by 2. Okay. In practice. But this is also hyperparameter that you can change. And during your project, you can try different hyperparameters here. Okay. What I'm doing here. Activation, right? Activation. Then we define the activation function. We use the ReLU function. Okay, this is all common practice. Doesn't matter. And then this is important. The input shape. Okay, it doesn't pop up. Input shape. What is the input shape? 32 by 32 by 3. I think, let me see, check. Yeah. So if we put our mouse here, we can see there's an input shape of the image, right? We can see 10,000. I mean, this is test. Wait, let's check the train. Okay. 50,000. We in total have 50,000 samples. And then for each sample, the size, I mean, the shape is 32 by 32, means length 32, width 32, and 3 channels, means 3 colors, the RGB colors. Okay. 就是长宽，还有它那个红绿蓝3种颜色，对吧 ？OK， why I said this input shape? I did something wrong here. Oh, I forgot to put the equal. Okay. Okay, this is the first layer. This is like the input layer. Then we do the second layer, okay? So the second layer, usually after a convolution layer, we use a max polling layer, okay? Commonly, we use max polling. You can also use average polling. Polling. Okay, again, this is a 2D, okay? It's an image, so it's 2D. 2D, and I think we need to put like this, 2 by 2. Let me check the parentheses. It's correct. 1, 2, 3, 4. Yeah. Okay, so this is the max polling layer. To do downsampling of the image. OK， 是那个降维，把它那个特征图变小一点。OK， 变成原本的1/4，凹乘号就变成1/4。OK， and then we can put another convolutional layer. Another convolutional layer. Yeah. Okay. And then also in the middle layer, we can increase the size. Like this is the number of feature map. Okay. I hope you didn't forget. Okay, this is the number of feature map. A hyperparameter that you can adjust. You can also put like 128, doesn't matter. You can put 128, doesn't matter. But usually it is the power at it's the power of 2. Okay. Yeah. Oh, the n 次方是 2 n to the power the power of 2, right? I think so. Oh, the n 次方. Okay. And then we don't need input shape here because it's the layer in the middle. We don't need input shape. Okay, then another max polling layer. Max polling, yeah. And then the last layer, we can put another convolutional layer just as this one. We just copy paste this one. Okay. So this is like a model without, we don't have the output yet. Okay. What's the problem here? Max, I have some spelling mistake. Max, oh, should be this one. Sorry, max polling. Okay, then we can check the summary of the model. Like we can check the structure of the model with the summary. You can see here. Then it will show you the output shape of each layer and then how many parameters we have in each layer. Right? So this is, and also sometimes it's also show you the size of your model. Okay. So the size of the model, the limitation of the size depends on your application. I mean, at this stage, you don't need to care about this. Okay. So usually this one, we call it an encoder. Okay, this part. Usually we call it encoder. 解码器. Okay. So you might, if you are going deep to machine learning or deep learning, you will know this word, encoder. Usually a machine learning model, a deep learning model is constructed by an encoder and a decoder. Okay. So encoder is usually used for feature extraction. And then here we have a decoder. We need the decoder. DCODR. Okay, decoder is used for, usually we refer it as a downstream, downstream. downstream. I think it's like downstream task. Okay, so the decoder is depend on your application. Okay, so if this classification task, usually we use like something like a softmax classifier. Okay. Okay, something like that. Then let's try to build the decoder. Yeah, very easy. Decoder usually has a very simple structure. I mean, in this case. So we put another layer. Because we already defined the model, okay? We already defined a sequential model. So now we can like directly add different layers to the model, okay? Different layer. Flatten. So we add the flatten layer first to convert this feature map to a vector, okay? 就相当于把这个特征图给它铺平，拉直，拉成一个向量，叫 flatten. And then we have some other layers, dense layer. Usually in the downstream task, we will put some dense layers. Dense layer, dense layer. This is also called fully connected layer. Okay, it's the same meaning. They have it has multiple names: dense layer, hidden layer, fully connected layer, and like a feed forward layer. Okay, so they create a lot of names. Actually, they refer the same thing. And activation function. Again, we use redo. Okay, and then the last layer is output layer. I just copy paste here. Output layer. The output layer, then you need to take care of this output dimension. So in this data set, we have 10 classes. So the output is 10. Okay, so what I mean is that for a neural network, the dimension of the feature map inside, I mean, in the middle of the neural network, you can change as you like. Okay, so for example, this 64, you can change to 120, 260, 256, doesn't matter. Also like this one, this one, this one, you can change as you like. Okay, but one thing you need to consider is that the input shape must match the real input that you give to the machine learning model. And also the output shape must match the task, the label of your task. Okay, like if you're doing classification, so you have 10 classes, so you put 10 here. And then if you put 20 and you only have 20, and you only have 10 classes, then there will be a problem. Okay. Okay, then we just run it. Okay, and then we check the summary again. Then we can see we have more layers here. We add the flatten layer, a dense layer, and another dense layer. Okay. Oh, so I can use the pen here. Okay. Okay, yeah. So from here to here, usually we refer it to encoder. And then from here to here, usually we refer it as a decoder. Okay. But the definition of encoder and the decoder is very flexible. Okay. Sometimes you can also say like this from here to here is encoder, this to here is decoder. Okay, something like this. It's very flexible. Okay, then let's compile this model. So to compile this model is to define the training, something about the training process, optimizer. Yeah, as always, we use add down. This you don't need to change. You can keep it as always, add down. And then we need to define the loss. Okay. The loss is important. Here we use a loss from the TensorFlow keras. So this is building. Some genius already wrote it for you, okay? Losses, okay. And in these losses, we have a sparse. Okay, I will explain the things later. It's called from logits. Yeah, from logits. From logits. Okay. So let's first talk about this line. You will see there is a loss function called sparse categorical cross entropy. Usually we say this cross entropy, right? And then when you're talking about cross entropy, you'll find two kind of, and maybe you can find more, okay? So, but I mean, the most basic things, most basic ones is like categorical cross entropy and sparse categorical cross entropy. What's the difference? So for sparse categorical cross entropy, your label must be integer. Let me show you. Okay, let's see. Let me try to plot one of the. Yeah. Okay. So if you plot this label, that doesn't work. Okay. String label. Oh, it doesn't work. Oh, yeah, it should be 0. Sorry. Okay, yeah. So if you check one label, so this is the first label of the sample. Okay, the label is 6. So it means we can also like check another one. For example, the second one. The label is 9. Okay, but it means the labels of these figures here are labeled from 1 to from 0 to 9, I think. Yeah, from 0 to 9. Okay, so here I can write something here. So this sparse categorical entropy is used for labels of integers like 1, 2, 3, 4, 5, 6, 9. Okay, and then also we have categorical cross entropy. If you look at the demo of the project I put in the OLE, I'm using this categorical cross entropy. And categorical cross entropy is used for labels with it's called one hot encoding, right? I think you are already very familiar with it. We've talked about it for many times. One hot encoding. Okay, so it will be something like 0, 0, 0, 1, like 1, 0, 0, and 0, 1, 0. Okay, something like this. It means for this label, it is a vector. And for this label, for sparse categorical cross entropy, the label is integer. Okay, so this is why we use sparse categorical entropy here. And cross entropy is just because we are doing classification task. That's why we use cross entropy, right? And also then you can find something called from logits true. Okay, so what means why we need this one? Because when we're doing classification, we need a softmax classifier. We need a softmax function. Okay, I hope you still remember softmax. Okay. So it map the value to a probability distribution between 0 to 1, right? So it's like you have an input output layer. Then you use this output layer as a numbers, doesn't relate to the probability. Then you need to use this softmax activation function to map it to a probability according to its value. OK， 因为你输出层的那个值一般都是些这种变量这些那个数值对吧？一些数值，但这些数值不是在0和1之间的，然后你就无法用它来表示它的那个概率值，所以你得使用一个 softmax 激活函数来把它转换成概率值。OK， 所以这个值越大，它的就说明它的概率越大。OK， 值越小就说明它概率越小，就是 softmax 函数作用。And then here, if we said from logits is true, okay, so it means what is logits? This is logits. The output layer, the values in output layer is logits. So if logits is true, then it means in your neural network structure, you don't have softmax activation function. Okay, so we can see here. Yeah, actually we are not able to see here, but we can see in the neural network structure. Oh, I made a mistake here, sorry. I made a mistake. We cannot use ReLU here. Okay, attention please, delete this one. Okay, sorry. So if we don't define the activation function here, like we don't define softmax here, then we need to put from logits equal to true. Means the output from the neural network is logits like this. Okay. However, if we put something like this, activation function equal to softmax. Okay, if you put something like this, activation equal to softmax, then you can put this as false. Okay, so something like this. Yeah, so you can choose either way, doesn't matter. Then we just start to train the model. Train images. So this is the training data we use, train images. And then the target value, train labels. And then let's save some time. We use like well, I think let's try first. Let's say we use 10 epochs. 10 epochs. And then we also have some validation data. Okay. It's validation data we get from the beginning. The first block of the code is the test images. And sorry, test images and test labels. Test images and test labels, right? Yeah, okay, then no problem. Let's try. Okay, no problem. Yeah. Very fast. So that this time we are using GPU. Okay, that's why it's quite fast. Mm, mm. Okay, then let's wait for 10 epochs. Oh, I forgot something here. I forgot to put the matrix. And that's why I was wondering why there's no accuracy. Yeah. Okay, but doesn't matter. We can say the loss here, okay? And then we can put also like a matrix here. The evaluating matrix. 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 METICS. METIC. Oh, why there's no matrix? Wait, let me check. Compare loss is here. All right, and then matrix. Yeah, now it appears. Matrix. Matrix equal to, we use accuracy. Okay. Uh, to see, yeah. And then let's draw for another round. Eh? Wait. Why the accuracy doesn't change? Some problem here. Sparse cross entropy. Oh, when I run this code, I think I didn't run this code. Maybe because. Yeah, I haven't run this code. Okay, sorry. After I change it to softmax, I forgot to run this code. That's why, yeah. So this is the thing, okay? That's I also want to talk about. So this is also like an example that if you wrongly set the front logics, okay, then you will see there's almost no training effect on the result. The accuracy never change. There's no gradient. Okay, this is because I was still using. I forgot to run this cell. Okay, so I was still using the previous one. I was using this version. So if you set this at false, then you must use softmax here. Okay, let's change back. Okay, let's say we don't use softmax here. Okay, we use softmax here. Logic is equal to true. Okay, then we run it again. Hmm? Wait. I think I need to wait. Let me rebuild the things. Oh, Yeah. So here's a problem. Yeah, another problem. Okay. So if you separately, if you put the code into separate cells, okay, then every time you run this cell again, you add an extra layer here. We can check it again. Like if we run this model summary, because we have a lot of more layers after the flatten. Okay, we're supposed to have only one, but because I run this for 2 times, and then it adds 3 more layers here. Okay, so this is a problem you need to take care. Okay, so if you find some mistakes here, then you need to redefine the sequential model again. Okay, you need to redefine the sequential model again. Here, you define a new empty model and then start to add layers. So in a common practice way, usually we put all the things together. Okay, usually we'll put like this. We will not separate them. Okay. In this lab, we just want to demonstration the difference between the code. So we separate them. Okay. But in your project or when you're doing some other tasks, you don't need to separate them. Okay. So let's do the things again. We run the things again. Then we can see it will be normal. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 layers. Then it's correct. Okay. Sometimes it's good to make mistakes because after you make mistakes, you know how to deal with the mistakes. And then you can see we have quite normal accuracies, 33%. Previously, we only have like 9%. So it's very abnormal. Okay, now we can see the accuracy is increasing.这边我再那个用中文说一下啊，就是之前那个问题什么原因呢？就是我这边我把这个模型分开写了，对吧？然后因为模型每次你定义的时候都会先定一个空的模型，然后再一层一层的加那个层数。然后因为刚刚我在这边运行了这行代码，运行了2遍，所以他就给它多加了3层过去。OK，然后我之前那个用 softmax 的时候，那个代码又忘记运行了，对吧？所以就连续做了几个错误的示范。OK，所以你那个自己做的时候，最好是把这个代码和这个上下代码合在一起。OK，如果这样的话，如果你发现这边有些什么错误，你不会，你可能会把它再跑一遍之后，你就忘记先跑前面的东西了，因为你每次你跑的时候，你都得先定一个空的模型。如果你直接加层的话，它就加在你已经定义的那个模型上面，就原本你就6层，你这边又说加3层，它就变成9层了。OK，然而你只是想要6层，对吧？所以你每次要记住，比方说你把它分开写了，你这边改了一下之后，运行了一遍之后，你要先把前面的运行重新定一个空的模型之后再运行下面。OK。Okay, now then we have quite good accuracy, 77%. Then we can do the last step to visualize the accuracy. Okay. So here we use model.evaluate. So it also check the test accuracy, test images, and test labels. Okay, and then let's see it. Let's see verbals equal to 2. Verbals equal to 2. So verbals equal to 2 means we only show the result, the final result. Okay. So we will see this is the final result. And what happened if we put verbals equal to 1? Then it will show you the whole progress. Okay, so it will show you the progress. And if verbals equal to 0, I think it will not show you anything. Yeah, okay, so it's like this. So we use verbals equal to 2 to see the final result. We have the accuracy, testing accuracy of 70%. Okay, and then we can see the history during different epochs from 0 to 10. Okay. And then I think it's quite good. We don't have a very severe overfitting problem here. Okay. So we have like a bit overfitting here. Actually, the optimal point should be here, the 6 epochs. Okay, but it's not very obvious overfitting because maybe later in the 11th epoch, it might also still increase. Maybe, I mean, this is possible. It's not a very severe overfitting. Okay. So also for your project, you need to check like these two curves to prevent your model from overfitting to your training data. Okay. Yes, I could print in the test accuracy. Yeah. So that's it. This is the things today for today's lab, and this is also the last assignment. Okay. Okay. So any questions? Okay, so if there are no questions, then it's the end of this lab. And thank you very much for coming, and see you next week. Yeah. Okay. Bye-bye.